Hi, I'd like to proceed with the lecture number 4. The subject of lecture number 4 is PWM switch model, which refers to the small signal model of PWM switch. This model is developed by Dr. Poporian, and he named in his paper this term, PWM switch model. He coined this term, so this is considered as a proper noun, PWM switch model. Okay. In the last lecture, we went through all the details about the linearization process of nonlinear relationship. We discussed 3 different approaches. First one is truncated Taylor expression, and second one is local slope concept, and the final one is this one, and perturbed expansion of some nonlinear relationship. So we'll be using the last concept. So we'll apply that step, the perturbed expansion concept, to the averaged PWM switch model. Okay. So this is the averaged PWM switch model. We discussed this maybe 2 of previous classes. So this is active terminal, and this is passive terminal. Common terminal is always combined with the inductor, and active terminal is interfacing with active switch, and the passive switch diode is coming here. Okay, so this is the equation of this model. So we used ideal transfer model for this, but here we consider this expression. So this is the mathematical expression of this operation. The averaged operation of PWM switch, VCT bar is dt times VAP T bar. Okay, here everything is time-varying variable. So we have 2 equations for this. One is relationship between this voltage, and the other one is current relationship between this and this. Okay, so we perturb this. So let me take one example. One specific example, equation number 1. So equation number 1 is expanded out in this manner. So VCP consists of this DC component, fixed value, and the small signal AC component. And the duty ratio is, this is the steady state duty ratio, D plus some perturbation, AC perturbation, sinusoidal perturbation in duty ratio, and the VAP is also combination of DC component and the perturbed component. Okay, and you just expand out, you have this. So this is the DC term. You are not interested in this term, and this is the second order term. This D hat is very small, and the VAP hat is very small. So multiplication of 2 small variables can be considered very small. So we ignore this and collect only this first order term of AC component. So we have VCP here, VCP hat, and this is the first order AC term, and D is the coefficient of this, and this is AC component. VAP is DC component. Then relationship is this one. So by collecting this and this, equating in this manner, you have this equation, and we apply the same step to the equation number 2 to obtain this. Okay, so this is the small signal equation of PWM switch. Okay, everything is, so far we only considered this time varying function. So I omitted the t here, but assume every variables are defined in time domain. Later on, we will convert this thing into the S domain. Okay. So VAP hat is a combination of D hat and VAP hat. It's linear combination, and the weighting factor is this VAP and the D. This is the DC information, DC variable. Same is true. IC is DC component of this current, C current going out from the C terminal, and this is the steady state duty ratio is also DC component. So this variable in the small signal model, small signal variables are expressed with linear combination of other small signal variables, and the DC information is used as the coefficient of this. So this small signal model depends on DC operating point. So this DC information must appear here. If you linearize something, there is no DC component. That means the original equation was already linear equation. So you don't linearize the linear relationship, and result becomes linear. Okay. So for the older linearization process of nonlinear equation, the result should contain this DC information always. Okay. That is true for any linearization process of nonlinear relationship. Okay. So this is the equation of this nonlinear relationship, and this is a circuit model. Okay. So in this lecture, you easily confirm this their equivalent, and this the circuit relationship between circuit variable between this and this current and this current is exactly same as this. So this is the circuit representation of this, and this is called, named or coined PWM switch by Dr. Poporian. So PWM switch model refers the small signal model of PWM switch. This is the buck converter example. Always I'm using buck converter example as an example, but you know this can be generalized to any PWM converters, and the details about that will be discussed in the upcoming lectures. Okay, so we have this buck converter, and we have this PWM switch, and the small signal model of this is simply obtained by replacing this with this pin-to-pin fashion. So this is the small signal model of buck converter. So PWM switch model is here, and the remaining part is, it was the remaining linear part of buck converter. So originally it was VAP. For this case, VAP is this one. For the buck converter, VAP is voltage across A terminal, and the P terminal is input voltage Vs. Okay, and this IC is defined as the current coming out of C terminal. So this is same as IL. Here IC is replaced with IL, and this D hat S. Okay, so all the variables are expressed in terms of this S. S is complex frequency, and in particular S is this one. S, oh, let me use this. Okay, so S is sigma plus J omega. For the sinusoidal analysis, this is 0. Okay, so now S is simply J omega. So this is S domain or frequency domain model, and simply L is replaced with SL, and this capacitor C is replaced with 1 over SC, and we have S here everywhere. We used the notation S, implying this complex variable. Okay, so the next slide start with derivation of this, and we'll discuss the generality of this extension of this model to other converters, and we evaluate the validity and accuracy of this model using the computational method with some software, and comparing the result, Bode plot of transfer function of this converter with this model, this small signal model, which is linear time invariant. Okay. This is the second part of this lecture. So in this part, we'll apply the previous linearization step to the average model of PWM switch. This is circuit model. So, but it is not. It's much more convenient to use this expression equations to linearize it, yes, which is the same thing. Okay. So we use this first equation. So this is the nonlinear relationship VCP. Maybe I ignore the bar sign here. Everything is averaged variable. So even though we skip this bar here, everything means the averaged variable. So you have this, then this VCP bar is decomposed this DC component and the AC component, and the D is also decomposed into the DC duty ratio and the small signal duty ratio, so on. And you expand this out, so you have 4 terms, then you ignore this, and you take only 2 terms, and you take this one. So this is the AC equation of this one. Okay, small signal equation, linearized equation of equation number 1 is shown here, and you repeat same procedure with this and same thing. This is the AC equation of equation number 2. Right? So you have 2 equations, linearized small signal equations for the AC component. So you are not interested in DC component, and you ignore the second order terms. There is just some error, but error is negligible. You are assuming this is so small, this squared term can be ignored. Okay. Then, and also this VAP and D and the IC, they are all DC information. Okay. Every small signal model of nonlinear relationship should carry the DC component together. Okay. So otherwise, you linearized already linear, something like that. Okay. For the linearized nonlinear equation, always carry this DC component. Otherwise, something is not right. Okay. So this is very easy, and this equation, this one, 2 AC equations are combined together. So this is the AC equation of PWM switch. Okay. So VCPT is a function of DT and VAPT. Okay, and this is the coefficient of this, and also same is true here. IAT AC component is this term originated from this small signal duty ratio and the small signal IC. Okay, all right. So this is the AC equation of PWM switch, and because we like to have circuit model of everything, so always we are dealing with the circuit. So this is the part of PWM converter, which is circuit. So circuit model is much easier to memorize and to deal with, and most favorably, this circuit structure is directly programmed or combined with programmed into your circuit simulator. You don't have to change anything. That circuit simulator accept this one as it is. Okay, and the guy who derived this is the Popolian, and this is his book. This book is good. It's a good book. Title is Fast Analytical Technique for the Electrical and Electronic Circuit. So this book mostly deals with, this is the design-oriented analysis. I think I mentioned this several times, as proposed and advocated and promoted by Dr. Middlebrook. Okay. What we are doing is very similar to this. We are using asymptotic analysis, okay, and we are using graphical approach, and we don't need some unimportant details, and we use graphical method is the essence of this approach. And this is called extra element theorem. This is advanced circuit theorem, which is very useful for power electronics. And he wrote this book about 20 years ago. I used this book in my graduate course as a text, and I found many typos and mistakes. And I mailed that to him. Okay, I don't know he corrected that one. This one. Okay, I said this equation and this circuit model is exactly the same. Let me check that out. Okay, VCP is voltage across this CP terminal. And when you are considering this, okay, we are considering this VCP and VAP, assume this one is deactivated because we are using the principle of superposition because this is a linear circuit, okay? So when evaluating this is 0, so this is shorted, this is opened, then this voltage here is multiplied with this D, okay? So this is the first term, and the second term here, so this is activated, and this one becomes active, and this one becomes 0, okay? They are shorted, then this current is just circulating this. There is no reason this guy will go to this direction. It's shorted. There is something, okay? So it's just circulating this, okay? Then this and this is shorted. Then voltage appearing across this primary winding of this primary side of this ideal transformer is this one, and multiply with this, okay? There is this one, okay? DD, they cancel, and I swap the, this is okay, right? So this is the first equation, this one. And the second equation, IA, is this one, plus IC is reflected by this duty ratio. So this is this one, and the second term is this IC hat is reflected by this, okay? So this is nothing, this voltage source is, this can carry any current, okay? So this is okay, so this is, okay, they are same thing, right? And the beauty of this is real value of this PWM switch will be shown in the next slide, okay? So this is a summary, okay? I showed this, the beginning of this lecture, the glimpse of our goal is we reached this equation is linearized to yield this PWM switch model, okay? So using this model, small signal model of buck converter is shown here. So A, P, C, and you just replaced this thing with this PWM switch model. P2 pin replacement of this will generate the small signal model of this converter in terms of time domain format. Okay, this is time domain format. All right. Maybe this model might be good for the time domain simulations when this disturbance here is very small, so it doesn't perturb much the DC bias point. So then this will be used to simulate the time domain response of this. All right. But the more useful, more informative, or more valuable form is this one, S domain model. Okay, very simple. Just replace this T with S. All right, just switching these variables, and everything remains same. And this L is SL, and this is the 1 over SC, and then this is the S domain small signal model of buck converter power stage. And you perform the circuit analysis of this, then you generate the transfer function of this. If you obtain the Bode plot of that transfer functions that portray what frequency response of your converter in the same manner as the linear time invariant system. Okay, we have seen that so many times in the previous topic. All right, so we first investigate, assuming this one will come later. So now we have this small signal model of buck converter, and can be generalized for 3 basic converters very easily. So this is the small signal model of buck converter. Okay, so AP, DC voltage across AP terminals, input voltage Vs, and IC is IL. Okay, so this is the small signal model. So here again, this D, duty, steady state duty ratio is coming along with, together with the inductor. Don't use D21 is wrong. Okay, so always D comes with this inductor here. This is the boost converter model. Okay, boost converter. This is the common terminal, and this is common. This is active. This is passive terminal. Okay. this voltage is minus VO. So you swap the polarity of this rather than putting minus sign in front of this, same thing, but this one is combination, okay? And here, IC and IL, they are opposite in direction. Then don't put negative sign here, just to rotate, the swap, the position of the arrow, then becomes the small signal model of boost converter and the box converter. Voltage across this AP is this one, and in here IC is the same as IL, and for the all converters, this D comes with this inductor, okay? And frequency response of power stage, this is a frequency response, all right? You know what frequency response is. So frequency response is this one. This is a transfer function, and when evaluating these transfer functions, this input is active, and the other two inputs, this and this, they are dead, okay? So it becomes 0. So because of the superposition principle, so then with this one is active, the other two are dead, you have due relation to output transfer function. Then if you have these transfer functions, and you just replace S with J omega and plot the Bode plot, that is the frequency response of this. You know the meaning of this, and you know how to interpret this, okay? You went through this several times, at least 2 times, okay? So now everything becomes everything is coming all together. So let me elaborate just 1 or 2 things, okay? This one is easy, okay? Suppose when Vs is 0, okay? So Vs head is 0 during evaluating this one or this one, then Vs head is 0. Then this current is circulating through this. So it does not go into this power stage, okay? So in buck converter, this is nothing, okay? They are there, but they are just circulating, okay? Another thing is if this is the 0 and this is 0, okay? Vs is 0, this is shorted, and D head is 0, open shorted, means this primary winding of ideal transformer is shorted, then secondary winding of ideal transformer is also shorted. So everything is shorted, okay? So when evaluating the transfer function from here to there, this circuit reduced just like this, okay? I need R here, load resistance R, all right? So this parallel combination of this is what? This is a parallel resonance circuit, okay? Forget about that, okay? We are talking about the PWM converter, and with this, then you can sketch the asymptotic plot of this, and you can easily evaluate this Q, quality factor, and the output frequency. So everything becomes so simple, okay? So there is just some parasitic resistance. Then you add the resistance here, okay? So this topic will be covered next, right? All right. Then I have some example, simulation example. So GBD of practical buck converter. Practical means, I said ideal means RL, RC, they are both 0, okay? I just ignored the parasitic resistance, and this practical means both RL and RC is considered, and here we have 2 models, okay? If you go type this, I provided all the PSIM files. So search this name. So this comes together. There is 2 in one file. The upper one is switch model to simulate this with computational method, okay? Just repeating time domain simulation over and over again, and get the measure the ratio of the input and the output, and the phase delay between the input and the output in the same same way as the impedance analyzer does. Okay? Understand this, right? So this is different. This is just measuring this using this software, and this is the small signal model we developed. Okay? This is the ideal transformer. In PSIM, there is no ideal transformer. So I used some this voltage source and current source, and I think I sensed some current somewhere. I don't know. Okay. Anyway, this. Oh no. This is not ideal transformer. This is something else. This is the ideal transformer. So this ideal transformer with very large magnetizing inductance, something like that, or ideal transformer. I don't know. Maybe it doesn't look like ideal transformer. Okay. Anyway, I used this. All right. This is okay. Let me show this. This is the small signal model of power stage. So this is this, and this is two dependent sources. This is a voltage source, and this is a current source. Okay, and this is the IL, which is the output current, same as the output current in the buck converter. So this is the output voltage, and this is the load resistance, which is 4. This is IL, average value, and I used this. This is the modulator. I used this, okay, very simple modulator. And the height of this one is 3.8. So modulator gain is 1 divided 3.8. Okay, we'll discuss this later. I'll clarify this. Assume this is correct. And this is the small signal is coming in and coming out. Okay, so here, this is the AC signal. So by directly measuring this, you have this Bode plot. All right? So you don't have to use this small signal model. This is just to show the idea. So you can implement this with the PSIM. This is time domain model for the computational method. This is switch model, and this is the small signal model, and this one is direct duplication of this, and this one is something else. Okay? Let me show the simulation result. Here, this one is output voltage of here, output voltage of the here, and you need to consider this modulator gain, all right? Because what you are seeing here is this, for example, this one, VD, which is same as VP. We are using this term in the past, times FM times GVD. Okay, so to obtain this, you should divide this one by this. Okay, so you have minus sign here. The division becomes subtraction in log scale, and this is 1 over this. So this becomes negative number. So this becomes positive number actually. So 12 dB is raised, and we have this, and we have this. This green curve is from this one, which is ideal one, and this is something else. This is some noise and maybe some impact of high frequency pole somewhere here due to the sampling effect of PWM modulator. Understand this? All right. So they're same thing. Okay. It shows the model is very accurate. And another one is this one. In here, I simulate the GP, open loop load current to output transfer function. For this, we need this, right? We need 1 ohm of this, and just measuring voltage across this. It is the output impedance, and this is the AC disturbance coming in. And this is switch model. This is the open loop, right? And this is the duty ratio. And duty ratio of this one is 0.95 is 1/4. I select this number, so this is the duty ratio. Okay, I forgot to mention this. This is steady state duty ratio is coming here, of course, right? And same is true here. But this one. But difference is in this switch model, we should have this. But in this small signal model, we don't need this. Right? Just perturb this current source. This current source is derived by this voltage source, which generates the sinusoidal perturbation, is converted to the current disturbance using this functional block. Okay? So this is the result. This is the open loop output impedance. We know this. The low frequency value is just this one, and the high frequency value is just this one. Okay? So low frequency value and the high frequency value, and this with this noise is this switched model, and this continuous red curve is this ideal small signal model. Okay? Right? Small signal model. Okay? Understand? Okay. So you trust the small signal model, right? I didn't believe this for a long time because when I was studying this, I read one paper from the MIT people, and they claim that this model is wrong. Okay, we can find the case of wrong. Okay, but 90% is correct. Okay, so maybe 1 or 2 years I didn't believe this. I was in trouble. Later on, I studied all together. So this is a reasonable, very good engineering approach. You trust this, okay? All right. So this is the basically end of this deriving small signal model of 3 basic converters. But still, we have some job remaining. We want to extend this for the general cases, all right? So in my book, I wrote down that. So this is very simple, very easy to understand, to follow, and to use the final model. But 3 things need to be considered. The first one is the case where the reactive component, inductor or capacitor, has the ESR, all right? ESR. Your initial intuition is to place them at the original place in their original form. That might be true, but can be also wrong. Okay, so there is a special case to worry about impact of this, and another one is the DCM operation. So we didn't cover DCM operation. So DCM operation, power stage waveforms are entirely different from the CCM operation, and the equation of this average equation and the small signal equation are entirely different. Transfer functions are also different. They are different. Okay? So how to consider this is the second one. And the final one is there are many variations of PWM converter with transformer insertion. Okay? So isolate PWM converters. So how to extend these Beijing models to these 3 different cases are very important. Okay? Those things are completely covered in my book. Okay? So I'll go through this this Thursday, but let me introduce just this one. This one is the special case, very special case. So this is the buck converter, and this is derived by ideal voltage source. This is the impractical. Most cases, you should put some filter stage. I'll explain that later. Okay, without this infilter, buck converter with ideal voltage source, without any filter stage in between, then this is the same, right? Because VAP is this one, okay? Then VCP is just this one. So everything remains same. The average equation of a PWM switch remains the same, okay? Nothing will be changed. And for this case, the plastic resistance can be placed in their original location, in their original form, because the plastic resistance does not alter the circuit equation of PWM switch. So they can be added as just add-ons to the converter models. Okay, this is the case. All right.